So here's another problem just like the one we did. If we start with 1 gram of cobalt-60, 0.351 grams will remain after 8 years. So how long is the half-life in years? So I'll give you 2 minutes to solve that one. Okay. So just like we did on the last time, we first need to solve for the rate constant K. We're going to take our ln. We're going to take our initial mass of cobalt-60, which is 1 gram. It says that 0.351 grams remains after 8 years. Okay, so if we plug all of those values into our rate law expression, and solve for the rate constant K, we should get K is equal to 0.131. And then from there, we can solve for the half-life. T1 half is equal to 0.693 divided by the rate constant K. So that's 0.693 divided by 0.131, and we should get 5.3 years. Questions on that? Is it bringing back memories of chapter 14? Hopefully? Okay. All right, one more. This is kind of working in the reverse direction. Here we have cerium-131. We're given the fact that it has a half-life of 9.7 days, and we want to determine how much cerium will remain after 45 days. So now we're going to use our half-life equation first. And we're going to solve for K. So K is going to be equal to 0.693 divided by T1 half. And we should get a rate constant of 0.071 inverse days. So using that half-life equation to solve for the rate constant, after that, we can then use our rate law expression and determine the amount or the percent that remains after 45 days. So now that we have K, we can plug that into this equation, and it's in days. We want to know what happens after 45 days. What should we use for n sub 0? Yeah. 1 or 100. Beautiful. Let's do 100 because that's what I have in my notes. So we're going to figure out a percent, all right? So we're going to start with 100%, and then we're going to solve for n at time t. Taking the multiplying both sides, or multiplying the right-hand side, taking the anti-log, we're going to get e to the n over 100 equals e to the minus 3.21. And, e of the ln, sorry. That means n sub t over 100 is equal to 0.040. Multiplying by 100 then, we're going to get an n sub t equals 4. So 4%. All right. Questions on that? Okay, we'll do our last fun thing here. So I brought in, or I didn't do anything. The demo lab brought over a Geiger counter for us. Geiger counters measure nuclear radiation. They measure gamma rays, beta rays, and alpha radiation. So I have 3 different samples here. Sodium chloride, sodium iodide, sodium chloride, sodium iodide, and urinal nitrate, uranium. I also have lead sheet. And so I'm just going to show you a couple of things. I'm not going to open the uranium for my own health. But when I put this next to a sample that is emitting radiation, it'll make a very loud sound, a beeping sound. So we're going to start with the sodium chloride. This one I'm not sure. And so neither sodium or chloride are radioactive. So we don't hear anything from the Geiger. What do we expect from sodium iodide? Alright, let's try it. Yeah, nothing from sodium iodide. Alright, so then let's go to the uranium. We know this is radioactive. What's going on with our Geiger? I'm not opening that, though. This should work. This should be much more dramatic. Okay. I'll also show you. So this is a Fiestaware plate. I don't know if any of you have Fiestaware at home. This is a plate that was made in one of the times listed in those time blocks there. I don't know which exactly, but it has uranium in the plate. Okay? And it was one of the first Fiestaware plates that was made. It would contain a natural uranium straight from the earth. World War II then happened, and all of the uranium that we had was used to make nuclear weapons. And so, because of that, folks who made ceramics had to take the depleted uranium and use that in insulation. So that's what you see later on, 1959 through 69, depleted uranium. a different type of red was also uranium copper. So this should, I did this the other day, so I know this one works. There we go. So I will open that uranium, much as I don't want to. So that is what the uranium will sound like. And the lead blocks the radiation. Very well. Okay, we'll open it. Let me actually put it on TV. Especially now y'all have those out. It's gonna get me in trouble. I mean, this bottle of urine is maybe the top layer needs to be stirred up a bit. There we go. Yeah, that's pretty good. Does not work really well. Great, good blast. Good job. Okay. Take these. I brought a banana too because we talked about potassium. Sorry, not as exciting either. Yeah, so quite cool, right? So this is great Thanksgiving dinner conversation if you want to avoid politics like I will. So these still were plates. This is like the red color that was in the 30s. 50s, 60s, 70s, they stopped making this color, of course, because of uranium, which we realized how much uranium was in there and what it actually does. There's actually 4.5 grams of uranium per dinner plate, so that's a good pile, right? This bottle was probably like 500 grams at one point. Maybe so. They stopped using uranium. There are other metals that are used now to make glaze. No uranium. They use iron, cadmium, copper. Yeah. Questions? All right. Thank you all. Have a wonderful Thanksgiving. Let me know if there are problems you want me to work on.